Welcome back to Linear Algebra. I'm Dr. Jeff Grove. Today, we're going to talk about subspaces. We'll begin with the definition. A subspace of a vector space is a subset that is also a vector space in its own right under the inherited operations from the bigger vector space. Let V be a vector space. We see that W is a subspace of V if, first of all, W has to be a subset of V, and W is a vector space in its own right under the inherited operations from the vector space V. There are some things you need to be aware of. Every vector space must have a zero vector, which means vector spaces can't be empty. They always have to have at least one element. In fact, a vector space could consist only of some zero element. That would work and satisfy all of the defining properties of a vector space. Similarly, since a subspace has to be a vector space in its own right, it too cannot be empty. Let me give you an example. Let's let V be R3. As a simple example, suppose W is the set of all elements of R3 of the form x, y, 0, where x and y are elements of the set of real numbers. Clearly, W is a subset of V. Everything in W is also in R3. Is this a vector space in its own right? It inherits most of the properties of a vector space, except for 4. It's possible that it's not closed. Is this closed under addition and scalar multiplication? The defining characteristic of this subset is that the third coordinate is 0. If you take two things with third coordinates 0 and add them together, do you get something that has third coordinate 0? And the answer is yes. That means that is closed under addition. Since the original set, R3, is associative and commutative under addition, this one will be too. We're using the same operations after all, and these lie in the other set. Most of the other properties will follow. The 4 you have to check are, is it closed under addition? Is it closed under scalar multiplication? Does it have a 0 vector? And does it possess additive inverses? Those aren't guaranteed by being a subset. Everything else will be. Property of 1, distributive laws, associative law of multiplication. Everything else follows by being a subset and inheriting the same exact operations from the larger set. We have closure under addition. We need to check the other 3 questionable properties. Let's check closure under scalar multiplication. If I take A times x, y, 0, do I get something with the third coordinate 0? And the answer is obviously yes. So when you rescale something in W, you get something in W. So we're closed under addition. We're closed under scalar multiplication. The 0 vector is in W because it has third coordinate 0. So the 0 property is also true. That only leaves additive inverses. But the existence of additive inverses follows from closure under scalar multiplication. That's because the additive inverse of a vector is always -1 times that vector. In other words, if I have the negative of x, y, 0, that will be -x, -y, 0, and that has third coordinate 0, so that has to be in W. In other words, W satisfies all of the properties of a vector space. It's a subset of a larger vector space. Therefore, W is a subspace of the larger vector space. We can get a picture of this vector space in this case. V is R3. W is the xy plane. A plane passing through the origin. Every subspace has to pass through the origin because 0 must be an element of a vector space. As a next example, let's suppose that W is the set of all x, y, 1. X and y are real numbers. W is a subset of R3. The question is W a subspace? The answer is obviously no, because it doesn't contain a 0 vector. Also, it's not closed under addition. Or scalar multiplication for that matter. Those closure laws seem to be pretty important when considering subspaces. Do you see why I put emphasis on including those in a list of 10 properties for vector spaces when we introduced the whole concept of vector space? Those two properties seem to be very important when it comes to considerations about subspaces. In the list of 10 vector space properties that we gave earlier, there are only 4 that are in question when we're dealing with a subset. The 4 are closure under addition, existence of a 0 vector, existence of additive inverses, and closure under scalar multiplication. All of the other 6 properties are automatically satisfied by being a subset of a larger set that satisfies all of those properties. We have to check these, but are there really 4 in question? Or do some of these imply others? For instance, if you're closed under scalar multiplication, when you multiply a vector by a 0 scalar, you get a 0 vector. So if you're closed under scalar multiplication, that means 0 has to be in the subset. Closure implies existence of 0. But closure under scalar multiplication also implies existence of additive inverses, because -1 times a vector is the additive inverse of that vector. That means you really only need to verify 2 properties to get all 4. We have the following theorem. Let W be a non-empty subset of V. This is actually two conditions. One, W is a subset, and two, W is not the empty set. W is a subspace of V if and only if W is closed under addition and scalar multiplication. It may seem like there are only two conditions, closed under addition and scalar multiplication, but there are really four conditions when you think about it. W has to be a subset, and it has to be not empty. This non-empty condition is actually quite important. If you have just the empty set is closed under addition and scalar multiplication. Because if you take two elements in there and add them, you get something in there. That's vacuously true because there's nothing in there. So the empty set is closed under addition and scalar multiplication. If you add two nothings, you get nothing. So make sure when applying this condition that you don't just check the closure laws. You also have to check that what you're dealing with is not empty. Here's an example. We'll set W to be the set of all 2x minus 1, 3x, such that x is real. Is this a subspace of R2? Well, if you add two things in there, 2x minus 1, 3x, and say 2a minus 1, 3a, do you get something in there? The last coordinates give us 3 times x plus a. Well, so far so good, but what about the first coordinates? We'll get 2 times x plus a, but we get minus 2. This is not in W. So it is not closed under addition. Therefore, it is not a subspace. As another example, I want you to consider the following subset of the set of n by n matrices. Remember, if we set V equal to m n n, these are the square n by n matrices. Recall that the trace of a matrix, suppose A is the matrix with coordinates aij, is the sum, as k goes from 1 to n, of a, k, k, the sum of the diagonal elements of the matrix. Let's let W be the set of all A lying in m n n, such that the trace of A is 0. Is W a subspace of the vector space V, which is m n n? If a matrix has trace equal to 0, we call it trace-free. We need to see if the trace-free matrices form a subspace of the set of square matrices. The first thing we should check is to see that the set is not empty. The zero matrix, the matrix with all entries 0, has trace equal to 0. Since all of the entries are 0, the diagonal entries will also be 0. And so the sum of the diagonal entries must be 0. Therefore, W is not empty. That's a good first check. Now we have to check the two closure laws. Let A and B be elements of W. When we add these, do you still get a matrix that's trace-free? Let's take the trace of A plus B. That's the sum, as k goes from 1 to n, of the diagonal element of the sum. I'll write that as A plus B k k, but that's equal to the sum, as k goes from 1 to n, of A k k plus the sum, as k goes from 1 to n, of B k k. But we know that the sum of the diagonal elements of A is 0 because it's in W, and the sum of the diagonal elements of B is 0. We deduce then that the set W is closed under addition. We only need to check one more property to deduce that W is a subspace, and that is it closed under scalar multiplication? To this end, let B be an element of W and A an element of the set of real numbers. Let's calculate the trace of A times B. This will be the sum, as k goes from 1 to n, of A, B, k, k. After all, when you rescale a matrix, it just multiplies all the entries by A, including the diagonal elements. So when we add the diagonal elements of the product, A times B, we end up with A times B, k, k. But constant factors pull out of sums. That's called the distributive law. And we know the sum of the diagonal elements of B is 0. So we get A times 0, which is 0. We deduce then that the set W is closed under scalar multiplication. The theorem says then W is a subspace of MNN. So the set of trace-free matrices is a subspace of the vector space of square matrices. Every matrix can be decomposed as a symmetric part and a skew symmetric part. Let me give you an example. Suppose I have the matrix 1, 2, 3, 4. This matrix is neither symmetric nor skew symmetric. A matrix A is symmetric if A transpose is equal to A. The transpose of a matrix is obtained by switching what you mean by columns and rows. It reflects through the diagonal, the matrix. If a matrix is not square, it still just switches rows and columns. So a matrix is symmetric. This has to be a square matrix. It's symmetric if its transpose is equal to itself. For example, 2, 3, 3, 2 has transpose exactly equal to itself. So this matrix is symmetric. Again, a matrix A, which is square by n, is skew symmetric if its transpose is the negative of itself. A classic example of a skew symmetric matrix might be 0, 2, -2, 0. You can see that its transpose is 0, -2, 2, 0, and that's the negative of the original matrix. Now I said that every square matrix can be decomposed into the sum of a symmetric matrix and a skew symmetric matrix. I'm going to show you how to do that. Suppose I set B equal to A transpose plus A divided by 2. What do I get? I'll get 1/2 times the transpose, 1, 3, 2, 4, plus the original matrix, 1, 2, 3, 4. That's 1/2 times 2, 5, 5, 8. And that gives 1, 5 halves, 5 halves, 4. Note that B is symmetric. Because if I have 1/2 A transpose plus A, and then take the transpose of that, the 1/2 comes out, just being a scalar of all the coordinates of everything inside, and I get A transpose transpose plus A transpose. Well, if I do the transpose twice, I put it back as the original matrix. So I get 1/2 A plus A transpose. Matrix addition is commutative. So I get A transpose plus A. I get the original thing, B, which tells me that after I make this a combination, A transpose plus A all over 2, I get something where B transpose equals B. It is symmetric, as we've seen in our example. We've seen how, given any square matrix, to construct a symmetric matrix from it. I'm going to show you how to construct a skew symmetric matrix from any square matrix as well. Suppose we set C equal to 1/2 A minus A transpose. What do you get here? In the present example, we'll have A, 1, 2, 3, 4, minus its transpose, 1, 3, 2, 4. When we subtract, we'll get zeros on the diagonal. A -1 here and a +1 here. So we end up with 0 minus 1/2, 1/2, 0. That is skew symmetric. That has to be true, because if I take C transpose, I get the transpose of A minus A transpose. The 1/2 comes out of the process. We end up with A transpose minus A transpose transpose, which is just A. But when you reverse the order of a subtraction, you get a minus. And that gives us minus the original matrix C. So we know how to use any square matrix to construct a skew symmetric matrix from it. So we constructed the matrix B, which was 1, 5 halves, 5 halves, 4. And we constructed a matrix C, which was 0, minus 1/2, 1/2, 0. Notice that B plus C is 1. 5 halves minus 1/2 is 4 halves, otherwise known as 2. 5 halves plus 1/2 is 6 halves, otherwise known as 3. And then 4. That adds up to the original matrix A. So we have a symmetric part and a skew symmetric part adding up to the original matrix. We've decomposed the original matrix into the sum of a symmetric and a skew symmetric part. Is that always going to be the case? If I take A plus A transpose over 2 and add that to A minus A transpose over 2, the A transposes will cancel, and I'll have half of A plus half of A. Well, half of them plus half of them gives you a whole of them. That means every matrix A that is square can be decomposed into a symmetric and a skew symmetric part. This fact was used by Einstein in his unified field theory. He decomposed his so-called unified field into a symmetric part, which gave rise to the gravitational potentials, and a skew symmetric part that gave rise to the electromagnetic potentials. In Einstein's unified field theory, the matrix was a 4x4 matrix, and so it had 16 components. Each component was a function of space-time coordinates, x, y, z, and t. Gravitation, under Einstein's general theory of relativity, has 10 gravitational potentials. You can check. A 4x4 matrix that is symmetric has 10 independent components. Also, the electromagnetic theory has, well, it has 4 potentials, but with some degrees of freedom involved. The skew symmetric part has 6 independent components, more than enough to account for the electromagnetic potentials. In our next example, we're going to set V to be the set of square matrices, and W is the set of all A in V such that A transpose equals A. These are all the square n by n matrices. And I'm going to ask the question, is W a subspace of V? There are 3 parts to check, remember. Is it empty? Yes or no? Is it closed under addition? And is it closed under scalar multiplication? First of all, here's our check. Empty? Well, the zero matrix has transpose equal to itself, and that means W is not empty. That's a good check. Now, closed under addition. Let A and B be elements of W. What does it mean to be elements of W? It means their transposes are themselves. So A transpose is A, and B transpose is B. That's what that means. Is the set of skew symmetric matrices closed under addition? Let's check. A plus B transpose. That is A transpose plus B transpose. Yes, the transpose operation distributes. Let me show you. We have A, B, C, D plus X, Y, Z, W, and we want to transpose these. Going to be the transpose of A plus X, B plus Y, C plus Z, D plus W, and that's going to be A plus X, under that B plus Y, and then to the right C plus Z, D plus W. But if you do the transposes first, you'll have A, C, B, D plus X, Z, Y, W. And when you add those, you'll have A plus X, C plus Z, B plus Y, and D plus W, which is the same thing. So the transpose will distribute across a sum of matrices. We've assumed that A and B are symmetric, which means A transpose is A and B transpose is B. But that just tells us A plus B transpose is A plus B. Therefore, A plus B is symmetric. That means A plus B is an element of the proposed subspace. There's only one more condition to check, and that is closure under scalar multiplication. If we look at A times A transpose, this just rescales all the coordinates. It's still going to just rescale all of the coordinates of A transpose. Since A transpose is A, we get the transpose of little a times big A equaling little a big A. Therefore, little a big A is an element of the proposed subspace, which means it's closed under scalar multiplication. Therefore, by our theorem, we deduce that W is a subspace of V, which was the set of all M by N matrices. W, remember, was the set of symmetric matrices. That's a subspace. I ask you, is the set of skew symmetric matrices also a subspace? I'll let you check that. A matrix A, which is n by n, is idempotent if A squared equals A. There are a lot of matrices that do this, not just the so-called identity matrix. So for example, consider the matrix 1, 0, 0, 0. If you multiply 1, 0, 0, 0 by itself, you'll get 1, 0, and then 0, 0. The matrix 1, 0, 0, 0 is idempotent. Let V be the set of n by n matrices, and set W to be the set of A in V such that A squared is A. So W is the set of idempotent matrices. I ask, is W a subspace of V? We'll see. The zero matrix is idempotent. Therefore, W is not empty. Always a good thing to check first. Now, is it closed under addition? The identity matrix is idempotent, but if you add the identity matrix to the identity matrix, what do you get? Something with 2's down the diagonal and 0's everywhere else? Is that idempotent? If I take I plus I and square it, I'm going to end up with 4's on the diagonal and 0's everywhere else. And that's certainly not I plus I. That means that this set of idempotent matrices is not closed under addition. Therefore, it is not a subspace. There are two subsets that are always subspaces of some given vector space. First, the vector space itself is a subset of the vector space. It's not empty because the original vector space is not. And it's closed because the original vector space is closed under both addition and scalar multiplication. That means the vector space itself is a subspace of itself. We didn't say anything about the subset being a proper subset. 2, the set that contains the 0 vector is a subspace of the original space V. We kind of think of this as a trivial example. Both of these are trivial examples in their own way. I want you to think about subspaces of R2. Clearly, all of R2 would be a subspace, and so would the set that only contains the origin be a subspace. I want to think about vectors that lie on a line through the origin. If you miss the origin, just make the dot bigger. If you add two vectors that go along that line, you'll end up getting a vector that's still along that same line. Even if you add a vector in one direction to a vector going the opposite direction, you'll still get a vector going along that line. It turns out every line through the origin of R2 is a subspace. You can see then the subspaces of R2 are of three different kinds. First, all of R2. Second, straight lines going through the origin. And third, just the origin itself. As we'll see, those spaces are two-dimensional, one-dimensional, and zero-dimensional, once we define what we mean by dimension. If you have two subspaces, is the union a subspace? Not generally. One space might be W1, another one might be W2. If you take something from the first space, say V1, and add to something in the second space, V2, by the usual notions of vector addition, by placing them tip to tail, you draw in the diagonal. The sum, V1 plus V2, is not in one of those two directions. You get something outside of that, which means that when we take the union is not closed under addition. Unless one of them consists only of the zero vector. What if you take the intersection of two subspaces? Let's take one space, W1, that goes to the origin, and another space, W2. The only point in common is the origin. So in this case, the intersection is the set that contains 0. That is a subspace. So it looks like in R2, the intersection of subspaces will yield a subspace. What about in R3? The subspaces in R3 are either the entire space R3, the origin itself, by itself, lines passing through the origin, or planes passing through the origin. Suppose I have a plane passing through the origin, and maybe another plane passing through the origin. These will intersect on a straight line. Planes intersect on a line. A line through the origin is a one-dimensional subspace. So even here in R3, it looks like the intersections of subspaces will yield subspaces. There's a common three-step practice in mathematics: exploration, conjecture, and then proof. We've explored what happens when we take both unions and intersections of subspaces. At this point, we're willing to make a conjecture that when we take the intersection of subspaces, we get a subspace. What is required is a mathematical proof of this fact. Proof. There are three things to check. for a subspace. First, is it empty? Notice that the zero vector from V has to lie in both W1 and W2. Therefore, this vector lies in the intersection, since the intersection consists of everything common to both W1 and W2. Therefore, W1 intersect W2 is not empty. That zero check is always a good one when you're trying to prove something about these vector spaces is non-empty. Now, we need to show closure under vector addition and scalar multiplication. Let U and V be elements of the intersection. Since U and V are in the intersection, that means they have to be in both. So they're both in W1. And since W1 is a subspace, it is closed under addition. That implies U plus V is an element of W1. But since U and V are also in W2 and W2 is closed under addition, that means plus V is an element of W2. Vectors that are common to both W1 and W2 are in the intersection. That means that the intersection is closed under addition. I'll write down that conclusion. Now we have to work on closure under scalar multiplication. So we'll let A be an element of our real field and U be an element of the intersection. Since W1 is closed under scalar multiplication, A times U must be an element of W1. Similarly, A times U must be an element of W2 because W2 is also closed under scalar multiplication. Therefore, AU is an element of the intersection because it's in both. That means W1 intersect W2 is closed under scalar multiplication. And that is the end of the proof. Let S be a subset of a vector space V. A linear combination, S doesn't have to be finite, it could be infinite. In R2, it could just be some blob. It could be anything. A linear combination of elements of S is a finite sum of the form C1 V1 plus C2 V2 to Cn Vn, where all of the CKs are in our real field and all of the V's are elements of the set S. We only want to consider finite sums for our linear combinations. Infinite sums involve limits, and we're not going to talk about limits. Now, the span of a set S, which is a subset of the vector space V, is denoted by the span of S and defined to be the set of all linear combinations of elements of S. Let's give an example. Let's let S be the set that contains 1, 0. The span of S is the set of everything of the form x0, of the form a scalar times 1, 0, such that x is an element of the set of real numbers. In other words, we started off with just this one vector in the set S. The span ends up being the entire line containing that vector that passes through the origin. If S is 1, 0, 0, 1, E1 and E2 in the vector space R2, then the span of S is the set of things of the form x times 1, 0 plus 1 times 0, 1. But that's just the set of all xy, such that xy are real, and that's exactly equal to all of R2. In this case, we started off with two vectors pointing in different directions in the plane R2. When we constructed the span, the set of all linear combinations, we ended up with the entire plane. Now, the span of the empty set is the empty set. Linear combinations of nothing is nothing. So, there is a theorem, though. If S is a subset of some vector space V and S is not the empty set, then the span of S is a subspace of the vector space V. This we can prove. In our proof, first note, S is not empty by hypothesis. Now, we just need to prove the two closure properties. If I have U, which is a linear combination, and V, which is also a linear combination, when I add them, what I get is the sum of a linear combination and a linear combination, which is still a linear combination. That means that the span is closed under vector addition. One more check. Let's look at A times C1 V1 through Cn Vn. If you rescale a linear combination, you get a linear combination. Therefore, the span is closed under scalar multiplication. We deduce then that the span of a set S is a subspace of the larger vector space V. And that's the end of the proof. In our next example, suppose our set S contains the vectors 1, 0, 0, 1, 1, 0, and 1, 1, 1. Question: is the span of this set equal to everything in R3? When we find linear combinations, do we actually go throughout the entire space? The answer is pretty easy to check. We'll take C1 times 1, 0, 0 plus C2 times 1, 1, 0 and C3 times 1, 1, 1, and see if we can construct an arbitrary vector x, y, z. This is equivalent to the consistency of the matrix equation 1, 0, 0, 1, 1, 0, 1, 1, 1 times C1, C2, C3 equals x, y, z. Is this consistent? If it's consistent, then there will exist a solution for C1, C2, C3, which solves this system. To check for consistency, let's construct an augmented array and find the reduced row echelon form. First, let's take negative row 2 and add to row 1, yielding a new row 1. That gives 1, 0, 0, and then x minus y. We'll still have 0, 1, 1, y, 0, 0, 1, z. Now we'll take negative row 3 plus row 2, yields a new row 2. We'll have y minus z in this spot, and then z. We did not get a contradiction. In fact, we get a unique solution. We'll have C1 equals x minus y, C2 equals y minus z, and C3 equals z. Since we have a solution, that means it is consistent, which means every vector x, y, z in R3 is in the span of the three vectors that form the columns of the augmented array, first three columns. We conclude then that the span of the set containing 1, 0, 0, 1, 1, 0, 1, 1, 1 is equal to all of R3. It shouldn't be too surprising that the span of a set containing three vectors can cover all of R3. It doesn't have to, but it can. You might ask the question, if you only had two vectors, is it possible for the span of just two vectors to cover all of R3? That doesn't sound like a very likely proposition, does it? But we will require a proof. As another example, let S be the set containing 1, 1 plus x, and then 1 plus x squared. Now, S is a subset of the vector space P2, the vector space of polynomials having degree equal to 2 or less. However, what is the span of this set? Can you reconstruct any polynomial in P2 by taking linear combinations? Let's find out. Let's suppose that we have C1 times 1 plus C2 times 1 plus x plus C3 times 1 plus x squared and ask, can you get A plus bx plus cx squared for arbitrary a, b, and c? Note that on the left-hand side, we'll get C1 plus C2 plus C3 plus C2x plus C3x squared. For which a, b, and c on the right can we construct a solution? Remember, two polynomials equal each other if and only if corresponding coefficients are equal. The ability to span P2 is equivalent to the consistency of the equation C1 plus C2 plus C3 equals A, C2 equals B, C3 equals C. Is this consistent? If If it's consistent, then there will be a linear combination that constructs any polynomial of the form a plus bx plus cx squared, which will imply then that the span of these three polynomials will equal all of P2. We can, of course, construct an augmented array. And then, with two elementary row operations, produce the reduced row echelon form. Negative row 2 plus row 1 yields a new row 1. Negative row 3 plus row 1 yields a new row 1. That gives us 1, 0, 0, 0, 1, 0, 0, 0, 1. This is still C, this is still B. We'll have A minus B minus C. We'll have C1 is A minus B minus C. C2 is B, C3 is C. Therefore, the span of that set S containing 1 plus x, 1 plus x squared, is equal to all of P2. We already know that the span of 1, 0, 0, 1 is all of R2. But what is the span of 1, 0, 0, 1, 1, 1? What if I throw in some additional vector? Can you get any less than all of R2? It should be clear that this gives you all of R2, but I want to go through this in detail. Suppose I have C1 times 1, 0, plus C2 times 0, 1, plus C3 times 1. Can I get an arbitrary xy in R2? Well, this is equivalent to C1 plus C3, C2 plus C3 equaling xy. This gives me a system of equations. We can write the augmented array as follows: 1, 0, 1, 0, 1, 1, xy. This is already in reduced row echelon form. We have a free parameter. We have C3 can be something like t, in which case C2 will be y minus t, and C1 will be x minus t. So C1, C2, C3 can be expressed in the form xyz, but add on to that minus t, t. So anything of the form xyz plus t times minus 1, 1 will give you adequate coefficients to construct some arbitrary vector xy in R2. We get existence. It's not a unique solution for C1, C2, and C3. We get infinitely many solutions, but it's still consistent, and that means the span of this set is all of R2. There are two more spaces we have to introduce that are going to be very important in the future development of the theory. First, I need to define what I mean by the null space of a matrix. We're going to assume that this matrix is M by N. It's the set of everything in Rn. Notice that A times X is defined because things in Rn are n by 1 matrices. What you get out when you multiply A by X is an M by 1 matrix. The 0 is going to be the 0 in Rm. So it'll be the vector with m zeros down a column. I'll denote that by 0 with the subscript of m. And is denoted by either n of a or, more descriptively, null of a. Now, the definition does not say specifically that the null space of A is a vector subspace Rn. Surely it's a subset of Rn. It is a theorem to prove that the null space of a matrix is a subspace of Rn. But keep in mind, the null space is everything that gets sent to the zero vector. But keep in mind that the null space of a matrix A is everything that the matrix A sends to the zero vector, everything in the domain that when you multiply by the matrix A on the left, you get the zero vector in the range. We'll have the following little theorem. Null space of A is a subspace of Rn. The proof is pretty simple. Let U and V be elements of the null space of A. This means that AU is the zero vector and AV is the zero vector. What happens if you take A times U plus V? You get AU plus AV, which is the zero vector plus the zero vector, and that's the zero vector. That means the null space is closed under addition. To show that the null space is closed under scalar multiplication, take a scalar times U, where U is in the null space. Since AU is the zero vector, and when you rescale the zero vector, you get the zero vector, that means AU must be in the null space of A. So the null space of A is closed under scalar multiplication. There's one thing we forgot. We forgot to show that the null space is never empty. A times the 0 in Rn will give you the 0 in Rm. Therefore, the null space of A is not empty because it has a zero vector in it. We deduce then that the null space is a subspace of Rn. There's one more space we have to talk about, and that's the column space of A. We're still assuming that A is m by n, m rows, n columns. It's denoted by the column space of A and defined to be the span, the set of all linear combinations of the columns of the matrix A. For example, suppose my matrix A is 1, 0, 0, 1, 1, 1. We've already seen that the span of 1, 0, 0, 1, 1, 1 is all of R2. Therefore, the column space of this matrix A is all of R2. Now, that means the column space is a subspace of R2. Is the column space always a subspace of Rm? The answer is yes. We've already proved that the span of a bunch of vectors is a subspace. We'll state this as a theorem. If A is M by N, then the column space of A is a subspace of Rm. And the proof, of course, is that the span of some set is a subspace. In this case, the set S is the set of columns of A, and those are contained in Rm. So the span of that set is a subspace of Rm, but that is the column space of the matrix A. And so that's the end of the proof. Remember that if A has columns A1, A2 to AN, then A times X, where X is going to be X1 through N, will be X1A1 plus through XNAN. That means when I take the matrix A times X, what I get is a linear combination of the columns. Therefore, A equals B is consistent if and only if B is in the column space of the matrix A. It has to be expressible as a linear combination of the columns of A. This theory builds on itself. We have a large number of definitions that we introduce in this course, and a large number of theorems. I suggest that you either make flashcards, or you make a page with a list of definitions, maybe more than one page, and then a page or more of theorems and their statements in full.